Okay, in this example, we've got a disk. The disk is attached to this arm OC. OC is attached to a vertical shaft. That vertical shaft, we'll say, is rotating with a rate of omega 1, like that. But as the disk moves around, it moves with no slip on this horizontal surface. Okay, so that gives the disk a spin about the x-axis, which we'll call omega 2. And what we know here is that the disk rolls, as I said, without slipping, and that disk makes a complete rotation about the x-axis in a time of tau. Okay, so what we know here is that omega 2 tau corresponds to a complete rotation, which is 2 pi. So from this, we can say then that the rotation rate of omega 2 then is given by 2 pi over tau. That's sort of the known information. So basically what we want to do is take that information with our moving reference frame equation and end up with an expression for the angular acceleration of that disk, which is going to be a vector. Okay. So what I'm going to do is attach an observer to the disk. Okay. So attach observer to the disk. I'm going to have a small XYZ axis, which is also attached to the disk. Then I'm going to have a fixed set of axes, big XYZ, which is attached to ground. In other words, big XYZ is fixed. And again, our ultimate goal here is to find the alpha vector. But in order to get there, we need to first find the omega vector. Omega is the angular velocity of our observer, which is one in the same thing as the disk. So since omega 1 is about this fixed axis of big J, and omega 2 is a rotation about this moving axis of I, and if you look at it by the right hand rule here, that says that omega 2 must be in the negative x, like that. Alpha, which is the angular acceleration of the disk, we do differentiation of that, omega 1 dot j plus omega 1 j dot minus omega 2 dot I minus omega 2 I dot. These rates are constant, so that's a 0. J is a fixed axis of rotation, so that's a 0. So all we have left is minus omega 2 I dot is omega cross I. Omega we had as omega 1 j minus omega 2 I. That gets crossed with I. I cross I, of course, is a 0. And so what we have here is a minus omega 1, omega 2, big J crossed with I. Well, at the instant that we have shown here, the axes are aligned, so we can replace this with a small j. J cross I is a minus k, so this becomes a plus omega 1, omega 2 k. So that gives us our expression. Unfortunately, all we know here is omega 2. We don't know omega 1. So what we'll do is use the no slip condition. In fact, what I'm going to do is call this contact point E. Velocity of E is equal to velocity of some point on the same rigid body as our observer. What does that mean? Well, it means that regardless of where that observer is on the disk, there would need to be a fixed distance between that observer and the point that we're going to choose. O fits the bill here, because regardless of what position we're in, that observer's the distance between the observer and O, or any point on that disk and O, remains a constant. So I can pick O. Velocity of E with respect to O relative plus omega cross R E with respect to O. Okay. O, the reason I wanted to choose O is because that simplifies things. That's a fixed point. The observer and E are on the same rigid body, so that's a zero. And since E is a no-slip point, velocity of E is a zero. So what we have here is omega, which is minus omega 2I plus omega 1j crossed with a vector from O to E. Well, O to E, we need to go in X, we need to go a distance of big R, like this, and in Y it's a minus R, lowercase r, j. So we cross these two together. We know that I cross j is a k, so this is R omega 2 positive k. J cross I is a minus k, so this is a minus big R omega 1 k. So what we see from this is that this number here must be a zero, because all the other terms in the equation are zero. So omega 1, therefore omega 1 is equal to R over R omega 2. In omega 2, we said, we scroll back up here, we see omega 2 ended up being 2 pi over tau. So that's what we get. Therefore, alpha, which we saw was omega 1 omega 2k, that's small r over big R 2 pi over tau times omega 2, so which is 2 pi over tau, so that's a squared k. So that's the angular acceleration of our disk. What did we do? Well, what we did was just very basic stuff we've been doing all along. What I did was I wrote the omega for the disk in terms of omega 1 and omega 2. Omega 1 is about a fixed axis, omega 2 is about a moving axis. So when we did our differentiation, we ended up with this. But the key point here was that we know that point E here is a no-slip point. So if I write the velocity of E in terms of O, and use the fact that E is a no-slip point, that's a zero. O itself is a fixed point, and since E is on the same rigid body as our observer, then the relative term is also a zero. So all that's left is omega cross R is a zero. So we took an expression for omega, we crossed it with R, and we found the relationship between omega 1 and omega 2. We used the known information to find omega 2 and substituted that all back in to get that.